This problem number 5. Let's work on this problem after the break. It's a cute little problem. All right, go take a break. Be back within 10. I listed everything given to us. All right, so linear densities usually use the letter lambda for it, so that's per unit length. But this one is expressed in terms of grams. All right, so let's express it in terms of kilograms. All right, so now we're good. All right. This is kind of like the multiple choice quality. Not that complicated. Once again, one of the best things that you could do, if you can, just visualize it. All right, that's just visualizing this sort of stuff goes a long way in terms of solving these problems. All right, so this is the current which is coming out of the page. All right, so at least we know what the current value is. So this is the current which is coming out of the page. This is a lot of current. So you don't want to be touching that wire under any circumstances. It's going to have weight. So what you need to do is generate a magnetic force opposing that weight. And the current is coming out of the page. So if that's the case, so what do we have? The magnetic field has to be moving in this direction. The magnetic field is moving in this direction. It's going to generate a force in the opposite direction. So that should oppose the weight. Okay, yeah, I think I'm happy with that. All right, so it's got weight, which is mg. And if the magnetic field is from left to right, okay, so the wrong notation, it should generate a magnetic force in the opposite direction. All right, so the question is the value of this magnetic field. So how much magnetism is required in order to create this? All right, so the net force on the y direction has to be 0. This is up, this is down. This is positive, this is negative on the y direction. Magnetic force is in the opposite direction. The weight is in the down direction. Net force on the y direction has to be 0 because it's not going to go up or down. There's not going to be any motion. We want this wire to be 100% suspended up in the air. So this needs to be 0. And it'll become 0 when the magnetic force equals to the weight. All right. So what do we know? We have an equation for the magnetic force. All right, so we have the current, the length of the wire that's placed inside an external magnetic field. So you got the sine of the angle. And we also know the weight is given by mass times the acceleration due to gravity. All right, so the angle is the one that we're interested in. So this is the angle between the direction of the current is coming out of the page, and the magnetic field. So what that means is this is going to be 90 degrees, and sine of 90 is going to be 1. So that's what we got. All right, so this expression is going to become 1. All right, so back substitution. So we have I, L, B on the left-hand side, mg on the right-hand side. All right, and we are still figuring out B. So isolate B. So it's going to be mg divided by IL. Okay, so we will have numbers for all the stuff that we're looking at. All right, so let's add on to it. So we got G, 9.8. Okay, so what else do we need? All right, so we got the current, 28 amps. We got our G, so that's 9.8. The current obviously is given. We've discussed that. We don't know what the mass is, and we don't know what ML is. Okay, but we know the combination of it, ML. All right, so this needs to be expressed in terms of this. And then we're fine. Okay, and then we'll have the numbers and plug in the numbers. All right, so we have M and then we have L. So it's going to be the same as lambda. All right, now you can plug the numbers in and you will come up with a value. All right.
And now flip it upside down.
You can literally come up with an answer. What? So you guys see it? charges in it, and then boom, discharge it, and this current. Okay, notice that you're able to change.
Increases when the magnetic field is approaching it. And then flip it the other way.
You put permanent magnets in the system because you're able to actually.
So it decreases because magnetic field
Okay,
is
notice
pulling
that the
force
weight
upwards.
changes. Yes, we're not able to generate enough current. I think they were able to get it up to 10 amps or something like that. And then the installation started to smoke at some point. All right, but you can clearly see the way the weight keeps changing. All right, so you can increase its weight, so there's going to be a downward push on the scale, or you can reduce the weight, which means that.
And then there is a current running through the wire.
Okay, notice that that's 10 amps.
Cool.
All right, so this was a cute little.
Okay, just go.
You're up to zero, yeah.
Okay, so which means that when you send these particles, they experience absolutely no resistance. So that current can persist.
So now flip it upside down.
You can literally come up with it. So if you could just come up with this room temperature superconductor and come up with a persistent current. Boom, discharge it, and this current is going to keep going.
So it increases when the magnetic field is approaching it. And then flip it the other way.
You put permanent magnets in the system because you're able to actually.
So it decreases because the magnetic field is pulling a force upwards.
It's kind of neat. All right, so we were working over at California. Somebody was working at on room temperature superconducting material. So we're trying to come up with something that they can levitate on its own. And the person is going to keep working on it. Cute. If you could just come up with a room temperature superconductor, you could literally levitate just about anything you want. Kind of weird. All right, they build technology to get there. It's going to get there within a few years. I think within the next 10 years. The physics of it is already here, so technology is not that far behind. Anyway, moving forward. This was a cute little experiment. Speaking of technology, guys, what is it that you would do with a device like this? Just study this, take all the time you need. I'll give you guys like 2 more minutes. Notice that you have a wire inside this magnetic field. As soon as you run a current through it, it's going to experience force of deflection in this direction, right? So it's just going to snap in this direction. So what is it that you can do with that? All sorts of applications. So what's the first application that comes to your mind? What do you think? All right, I got some ideas. It could be a nice nail clipper. This is the brightest idea. We just went from levitation to clipping nails, so practical uses. What else? It could be a little guillotine for mice. What else? All right, guys, this little device that you're looking at, that's the simplest thing. It's just gonna boom, it's just gonna snap up and that's it. That little thing turns into the electric motor in reality. So the electric motor, the idea behind it is like that. It's straightforward. In terms of technology, take a look at the speaker system. So you got this voice coil here. All right, the current can go up and down. You can keep changing the direction of the current up or down. The voice coil is going to go into this permanent magnet, or more like the magnet is going to go into the voice coil, which is going to be located right in the middle. All right, so it's a two-dimensional representation of what you're looking at on the left-hand side, three-dimensionally. All right, so you got these crosses here, which means that the current is going into the page. Here, the current is coming out of the page. All right, so you got a wire here, you got a wire here. The current is coming out of the page. The magnetic field is in the inward downward direction, so it's going to experience an outward force. The current going into the page here is, once again, going to experience a force in the outward direction. All right, so this voice coil, depending upon the direction of the current, it's going to experience a force in the outward direction and the inward direction. If you change the direction of the current, say about 700 times per second, you will get a vibration, which is 700 times per second. All right, this is going to replicate the sound that you're trying to generate. All right, so that's how these speakers work. It's the same, it's an application of the same concept. All right, so the biggest application of this phenomena is electric currents. Okay, the phenomena that we're talking about, being able to influence a current carrying wire using a magnet. It makes just about the entire 20th century technology possible because everything depends on motors. All right, so here's a simple motor, something that you could do, you could build at home. This is one of the applications. If we were to do a lab, this is one of the labs that we'll be doing at Wabanzi. All right, so what you need to do is just get yourself a coil. I'm just gonna go forward with it. And then you got your permanent magnet. And he's gonna set it up. Okay, so I'm gonna skip the details of it. And then, all right, so the next thing that you need to do is you got your coil of wire over here. You got your magnet down below. And then as soon as you run a current through the wire, this thing is going to start to spin. You have to kind of initiate it first, and then it's going to keep on spinning. All right, so this is known as, this is your motor. That's it. Okay, so all the motors work this way. So you got your coil wire. Place it inside a constant magnetic field. As soon as there's current, and you need to initially spin it, get it to spin, it's going to keep on spinning until the battery runs out of juice, until you run out of current, more like that. Let's put it that way. So how does the magic happen? All right. Before I say anything, just take your time to study this, figure things out on your own. And then we'll go over it together. How does the magic ever happen? All right. You got the three-dimensional view, and then you got the top view of the same thing. All right, so the current is going up, coming back down. You got this rotatable shaft, so this thing can rotate over here. And you got a single loop here, the current loop, which is placed inside a permanent magnet, and that's it. Notice that as the current is going up, using the right-hand rule number 1, inside a magnetic field, which is from left to right, this thing is going to experience a force. All right, let me check this. It's going to experience a force in this direction into the page. When the current is over here, it's going in the downward direction. Once again, using the right-hand rule number 1, it's going to end up experiencing a force almost coming out of the page in this direction. So what it does is just going to cause rotational motion. It's going to cause a twisting motion. So what that means is this coil that you're looking at is going to experience a torque, rotational force. All right, so that's the description that I came up out of this three-dimensional representation. Same description, illustrated two-dimensional. Now you're looking, you got the top view, you're looking down in the direction of where it says shaft, obviously. All right, so the magnetic field is from left to right. The current is coming out of the page. You have to use the right-hand rule. Once again, you'll notice that there's a force in the upward direction. The current is going into the page. There's going to be a force in the downward direction. All right, so by using the symbols that you're looking at. So this is, W is going to represent the width of this. You're looking at the width of the base of this, this space rectangle that we're looking at. I was going to say triangle. Shoot me. Anyway, so this is what happens after 10 hours of talking. All right, so this represents kind of like the width that you're looking at. And this is going to be your point of rotation, where the shaft is. Okay, now that we talked about that a little bit, all right, so once again, we will get to use the derivation from that chapter number 20 stuff. Okay, the details of the derivation I'm not going to care much for. All right, the whole idea is to come up with an expression for torque and then come up with something a little bit more practical. All right, so what do we have? You got the current just going around, looping itself around inside this magnetic field, which is from left to right. Okay, so W represents the width of this rectangle that you're looking at. As the current is going down, all right, so what happens to the current is going down? Whereas the magnetic field is going this way, current is going this way. All right, so it's going to experience a force in this direction, and I think this section is going to experience a force in the opposite direction. So this thing is going to start to spin. It's going to experience a spin motion. All right, ignoring the details, if there's a force acting on it in this direction with respect to the pivot point, if there's a force acting on it in the opposite direction, it causes a torque. And once again, I'm just completely ignoring the details because I want to come back down to here. So this is the expression that we will get to use for torque.